Okay, so it's good to have done the first talk first because this talk actually builds on that talk. So basically, Software and Systems is a program that I inherited about a year and a half ago. And I was familiar with it simply because I'd worked with Dave Luganville quite a bit when he was here. But what we wanted to do was to bring in some of the notions of some of the things you heard about in some of the previous talks, including mine earlier this morning, to the point where we can actually now think about software as a dynamical system as well. So I'm going to talk a little bit about how you think about software in that context and how you actually architect, verify, and validate software in that context. And that actually also is a new construct. Because in the software arena, very often a lot of the architectural design principles are about sort of design up front, verify and model up front, and then deploy and forget. That's kind of our approach today. And actually, there's an even more interesting paradigm, which a lot of people don't think about, but there's a really big human element in software. And let me describe that. So if you're, we'll call it a Fortune 500 software company, and you're going to deploy your new software, traditionally what you do is you go out and you produce an alpha and a beta version. And so you have a lot of people testing that code. And you send it out to all the people who are willing to do that for you. And you have a trial period of a few, however many months, while they find all the bugs for you. Well, that's that works well for that environment. Why? Because, they can afford to do that. There's no like, okay, if we don't finish it by next month, we're going to go another $1 billion over in our development program. I mean, maybe they will, but, in the context of defense systems, we actually have to deploy this stuff and make it work, and we can't afford to keep crashing our system over and over again and testing it. Because each individual system is increasingly of high value. I mean, if you take some of our aircraft right now, for instance, that's a really good case in point. So the crowdsourcing model for software, in the context of a lot of the Air Force problems, is actually it's not a good model for a lot of contexts that we have in software. And so what I'm going to talk about is how do we sort of go beyond where we are today in software, where we sort of architect the software, model it, verify it, and forget it, to more of a dynamical process where basically we can actually, on the fly, online, correct problems that occur in that software as they occur and as the environment changes that software operates in. And that's a big challenge in computer science. So to that end, these are the portfolio goals. We want to enable quantifiable performance evaluation of critical software systems, in many cases life-critical software systems for the Air Force. We want to manage software environments in order to preserve vital mission functions. Again, the mission rides on the software, just like it rides on all those other parts, the network, the hardware, and in many cases the physical architecture, like the aircraft. And then we want to comprehensively understand distributed effects in large software infrastructures to predict global system failures. So you have interactions just like you do in the context of networks, where pieces of software will all have their own function in infrastructure. And if the infrastructure itself changes, or the policies or the resources or the underlying constraints on that infrastructure change, basically you want to be able to adapt and deal with that. And so these are the sub-areas in the portfolio: models for composable dynamic software, dynamic formal analysis and verification, and online assessment and repair of failure. So the first thing we have to do is come up with constructs that enable us to be able to do this kind of dynamic assessment. Those are not just off-the-shelf solutions. We actually have to develop those. And then, of course, once you've set up the framework for that, we want to actually have formal analysis and verification as things change. Again, not something you can just get off the shelf. And finally, we want to repair things as they're operating, right? So if you have failures in your infrastructure, whether they're cloud infrastructures, aircraft, whatever system you're operating in, basically we want to be able to repair things as they go wrong so that system can stay up, so it's resilient. And this also applies again to the cybersecurity area. So software and computer science in a very sort of basic sense is an extremely large area. There's a lot of components to it. And so whenever you get, people start talking to you about what software really means in a large context, and by the way, this is a very high Air Force priority. I'm going to talk about kind of how the Air Force is looking at this in a general sense. We spent a lot of time with folks at the Secretary of the Air Force office, and including Dr. Mayberry, but also some folks in Steve Walker's office talking about this. So over here you have computer science research, and there's lots of pieces of this, and they're sort of described in many different ways. So we can talk about security vulnerabilities, we can talk about dynamic mission environments, heterogeneous infrastructures, resource problems, system management strategies. There's a whole host of ways you can describe and architect sort of specific software solutions to problems. And then over here are the underlying mathematical frameworks that underpin most of formal methods and verification and all the things that we computer science has rested on since its inception. And basically, making these two things intersect is, there are great places to go for a lot of, where these things intersect. But in general, on a day-to-day basis, when we architect and design software, these things don't, always architect or, intersect. They basically, a lot of companies have to get their software out the door. They actually have to, deploy this stuff, and they have to do it fast. And so, sometimes you trade off, doing the really formal analysis of the large infrastructure for, just getting it out the door. So what we envision is the ability to understand, what our dynamic software environment is. Then we basically want to online verify its properties, okay? And for this, you can use a measurement strategy here, but in this case, and this is back to a question I had earlier, we actually rely more on formal models in this context than we do measurement. Although I'm going to talk about measurement a little bit. But basically, as that software evolves, we want to understand what the dynamical state space it operates in is, and we want to architect our software to actually be able to adapt to that, to be able to sort of change as conditions change. And then if you want to plug some of those other methods that we talked about earlier in, there's a framework for doing it. OK, so I'll be a little bit more specific. I'm going to talk about each of these areas. These are some of the areas that are part of the program. And again, one of the things we want to be able to do is we want to put the hooks in place for this sort of dynamical analysis of the software. And just doing that requires new constructs. And we have a number of initiatives in that. So basically in some cases there are programming languages for this, but mainly they're language constructs. How do you actually set up an application program interface for this? What do these APIs actually look like? How do they, how are they architected in the context of the overall structure of the code itself? And then, domain-specific languages, which enhance capabilities for code generation. Basically, we want, specific languages that enable the ability to, again, put these dynamic analyses, procedures in place when we actually architect the code. The next part is we want to actually do our formal analysis and verification of the software. And we want to do it online. We want to do it as that software is operating. And so I'm going to talk a little bit about how we do that. One of the biggest problems with verification in really large software systems is the state space explosion. And we've actually had a lot of really good results in this. Lower dimensional ways of actually building models and doing verification in the context of really large software infrastructures. And finally, we want online assessment and repair of failure. And this is the most interesting one. In fact, this is the one where we've actually had some results that are going to get used and deployed very shortly. And I'll talk about that. And we work very closely with a lot of agencies in this context, particularly NASA. So I'm going to talk about how you sort of set your infrastructure up to make this happen, and then actually do online structural repair of software as conditions change. Before I jump into that, though, I'm just going to talk a little bit about, up front, some of the coordination we do. So I told you that I'm actually one of the co-chairs of the large-scale networking group for OSTP. I also sit on the high-confidence systems and software group. Okay? This is another NITRD group responsible for assurance of software performance. And so we coordinate, again, across all federal agencies in what each of these individual areas of research. The next thing, basically, is we are part of the ASD R&E Software Producibility Initiative, which is actually an initiative which is run out of Rob Gold's office at ASD. Okay? This is an initiative right now that basically is looking at, across the department, Defense Department, exactly how do we architect software and how can we make it more reliable and how can we reduce these really high overhead costs once the system is fielded, and then basically you have these really large integration and recurrent costs because the software is just not meeting our expectations. And then basically I mentioned the Secretary of the Air Force is very interested in this. Again, we work with Dr. Walker's office. And we also work very closely with the Cyber Physical Systems Group at the National Science Foundation, which is actually very implicit in the High Confidence Software Systems Group. And of course, NASA, which I've already mentioned. I just want to say that we also coordinate with these agencies as well, the Army Research Office, the Office of Naval Research, the National Science Foundation, and DARPA. So we certainly are aware of the landscape in software. And this is by no means a comprehensive list. So, systems and software has evolved. I mean that in a literal technical sense. I also mean it in a programmatic sense. And software models using adaptive feedback and complexity reduction. This is really where we're at with this program now. This is one of our big emphasis. Feedback and formal analysis and verification. Again, I mentioned this. I'll talk about all these. Adaptive repair and assessment of distributed software infrastructures. Okay. Now, specifics in the context of human interaction and human performance in the context of software, many of those things have been in the program, and we still have some of those in the program. I'm going to talk about some of them. One of the things in this area, though, is much of that is work that I actually am collaborating with folks like Jay and Joe on, so Jay Myung and Joe Lyons, in the sociocultural analysis. So this area actually is becoming more and more part of those programs, but we still participate in a lot of what's going on there. And then, of course, as Hugh mentioned at the beginning, agent-based approaches kind of going down. And if you're interested in why that is, I can talk about that. But okay. All right. So what I'm going to do right now is kind of set up this problem of understanding how to do dynamic software assessment and repair. And one of the biggest things that you saw in that first slide I showed you was the feedback loop. How do you actually create feedback loops in software where actual specific performance in that software architecture or basically the subroutines in the software is put together? And so Matthias Felleisen at Northeastern actually has something called software contracts. And software contracts are kind of a powerful tool because what they allow you to do is trace through individual subroutines in really large pieces of code and understand whether or not specific parts of that code have executed correctly. And if they haven't, basically you have a way of tracing exactly where in those subroutine structures the code has gone wrong. So, this is sort of a means of architecting model checking directly into the way the software, is constructed up front. So when the software is online doing its thing, basically you can trace in real time where things are going wrong. So this specific approach is a really powerful approach. It's actually getting integrated, and there's a website which a lot of developers are starting to use now, which actually you can take these contracts and embed them in many different types of existing languages. I think most of this is a lot of this has been in the context of C and C++, but there's a lot of object-oriented programming languages that are adopting this now. Okay. The next part of this, so once you've actually set up an infrastructure for doing that kind of dynamic checking, the next thing I'd like to be able to do is make it scalable. Okay, so I talked about the state space explosion in the context of these really large infrastructures. And scalable model checking is a means of actually taking this really ridiculously large state space, which if you're going to actually do binary level repair of executables and code, basically now I can actually get down to some fairly low-dimensional realizations of things that need to be repaired in these large infrastructures to keep them running. And so understanding how to get from this really large state space to just those really small critical pieces of executable that are really controlling whether your software stays up or not is implicit in what these guys are doing. And they have a very powerful satisfiability modulo approach to essentially making that happen. And it involves essentially looking at this whole software architecture as a nested or multi-resolution structure and really finding the really small components, the really compact components that really make the software stay functional, even under really large failures of the code. Okay, so, but that's now sort of the analytic approach to doing error correction or software verification. What we'd also like to do is look at the probabilistic approach. So if you model really large state spaces in these software architectures as now not specific binary realizations, but probability distributions of states, then you can actually get even larger sort of scalability in doing this model checking. But in this context, you actually have to do very careful analysis of the distributions and what they're representing in these large state spaces in order to make sure you caught the right thing. And a lot of this is actually implicit in software testing. So once I've created my software, and perhaps I'd like to measure it or just represent it, in this context, statistical software testing and measurement is, so Mira Cohen at University of Nebraska-Lincoln has actually put together a very nice construct for sort of identifying where in the software you actually need to measure or represent critical states. And she does this probabilistically because she knows that those states are going to change. She knows that overall in the architecture there's going to be a lot of states that may need to be monitored. So she has a very nice rigorous way of representing these states probabilistically. So and then she can actually trace, once the code's executing, where the highest probability of failure or the actual failure occurred in that software as it executes. So this is both a specification for putting together the representation of where those faults might occur, and it's a means of checking where they actually do occur as well. Okay, this is to a question Peter asked me actually. So the idea here is that you can think of all sorts of levels of granularity of system and software performance, but one level of that granularity is at the mission, right? So what I'd really like to do is guarantee that given that my mission rests on this very large heterogeneous infrastructure, and it could be actually other components like hardware or network or distributed software, how do I actually represent both structurally and algorithmically the performance of the mission over that infrastructure? So this group, including a couple of folks from the University of Nebraska and University College London, have actually put together a really nice framework for doing online mission analysis. So they can actually pinpoint where in the infrastructure that mission is about to go south, and then we can use these other tools that we just talked about for tracing back in that infrastructure where those faults and those changes actually took place to essentially cause failures. And this was actually demonstrated in the context of a distributed RPA UAV scenario, and they actually were able to pinpoint where that RPA actually went off course and did things it wasn't supposed to because of software performance errors. So this is actually pretty powerful stuff. Okay. So once I've actually set up the architecture for being able to dynamically respond to software problems, and then I've put together the framework for representing them in low-dimensional state spaces, or at least low-dimensional enough to make them scalable and tractable for the cases that we're going to be doing. Then what I'd like to be able to do is repair things, right? So I've identified where that problem is, and now I want to repair the code that's actually dying and either repair or replace it, either at the binary level or at the structural level. So sometimes I might actually do, I can actually use some sort of algebraic technique to actually do binary repair, or I may actually just replace modules that need to be replaced. However you do that, Scott Smolka from Stony Brook has actually come up with a very nice feedback mechanism for doing online repair, in this case at the binary level, of code. And in fact, there's a really nice mathematical formalism which is connected to the finite automata, the hybrid automata that I talked about that's going on actually out at Illinois at the Cloud Computing Center. So there is some nice connection there. And the idea here is that I can actually formally represent the states in this architecture that are being either compromised or they're being, they're just dying because, in the case of spacecraft, a lot of times spacecraft have random errors induced by the environment they're in. And so the idea here is that we can dynamically create this feedback loop that I showed you now to actually do the repair. And the really interesting part of this is we don't actually specifically have to know what we're going to fix a priori. So this doesn't have to be predefined with some very specific model. There are general principles of repair that are dynamic that can actually be integrated into this. And so you can think about this, self-healing is a kind of way overused term, but basically this allows the ability to dynamically repair errors that are happening in the code as it executes on platforms like this. And this is a joint project with NASA, and we're actually slating this work for the next generation Mars rover, which hopefully will be launched in the next several years. So it's found its way into practice for real. Again, we talked about runtime repair. And again, basically, we could do this in a statistical sense, like what module. So now we're looking at a sort of larger scale realization of the runtime repair. And we can actually start to identify what modules in my infrastructure are most likely to die when. And then we can actually represent how we repair them using these, one way to do it is using probability models. There's also analytic models for just characterizing the overall system architecture and then going after modules that tend to die first. However you do that, Professor Kirchhoff from UT Austin has a dynamic way of identifying which modules are most likely to die and then actually going in and fixing those. And so this is sort of now the macro scale version of what I just showed you. Now I can not just identify the specific subroutine and binary repair it, but I can actually identify which subroutine and where it's located. And finally, last but not least, back to the sort of mission state, or maybe something between the overall global architecture and the mission state. We have this ability, ability to do automated model revision. So I told you in the context of Scott Smolka's work that the model itself can change, right? The model of what you fix can change. So formally representing how your model changes and what you need to fix is a really different and interesting problem. I mean, we're sort of on the cusp of being able to really think about this holistically. So what I'd really like to be able to do is learn what it is that's most likely to fail or what's failing, and then dynamically repair that and actually learn how to do the repair from basic principles. So I don't have to store this really large catalog of fixes up front. I can actually dynamically go in, analyze what went wrong, and fix it. So now, back to my point when I started all this, in software today, instead of deploying these really large pieces of code out there and then having 1,000 alpha and beta testers sort of fix them for you, you can conceive of a day where you can deploy this stuff and the code actually, or the architecture actually fixes itself, and it can identify where to fix what's going wrong on the fly. And that's what I mean by this dynamic approach. And that's just because in the Air Force context, you're flying your aircraft along. You can't afford to have 6 guys beta test it while you're flying it. You really have to, it has to be able to function through all the problems that it's going to experience. And that's why we're going in this direction. OK. So we have a lot of collaborators in doing this. And these are just some of them. We certainly work with the Information Directorate. They are part of the Systems and Software Producibility Initiative with ASD. And so they actually helped write the BAA for that. And, but the idea here is that we are working very closely with them in the context of helping ASD look at software producibility, not just in the Air Force, but across the Department of Defense. And then, obviously, I talked a lot about air vehicles here. I mean, these problems, the air vehicles are a really critical, user, customer of these ideas. And so we spent a lot of time talking with them about how we can integrate these ideas into what they're doing. Certainly, the Human Effectiveness Directorate, automating more of the functions that humans were crowdsourcing to humans is a big deal. This generalizes into a lot of areas. It's not just aircraft repair, right? So how do we actually enable humans, fewer of them, to do more stuff? I mean, maybe that's the best way of putting this. And then back to the original thing that I talked about, some of the original things that were going on in this program. The human is an element of the system, okay? The human has control parameters. We can model those. And so understanding how the human as a control element fits into this overall architecture, and then how do we error correct what the human's doing is also a really big question. But again, that's, that work is now going more into our, the work that's going on in our cognition and decision and our, some of our decision-making work. So this is an evolving area, but it's an interesting one, and we're trying to exploit the most we can get out of what's going on within the DoD and other agencies as well. And then finally, robust decision-making, certainly, we have a lot of collaboration with them. And as these models get less defined, right, as the fixes get less defined, the divergence between learning and model correction or model checking is getting smaller. So as those two things get closer together, basically we're sort of converging. I wanted to talk about Scott Douglas's work because Scott Douglas is an RH, but he's also part of this larger process which is actually modeling the human as an element of your infrastructure. And so knowing when the human fails and modeling the human is just as important as modeling the rest of the system because the human is going to be operating it, particularly if he's a pilot, right? So we'd like to know where we actually, the human can, the human fails as well as the system fails. What is the human good at? What is the system good at? When do we need to correct the human? That's the issue, right? So this is being done, and actually they have a formal modeling language to model the human, which is kind of cool. We can do verification like that. We can do verification on the human based on that formal language. So there are formal constructs, formal languages for modeling human performance in the context of these really large infrastructures. And Scott's group is doing a really impressive job of identifying and showing how that works. RI. OK, so when we get into this big software producibility initiative, we have to take these tools that we've developed and put them into the infrastructure. We have to have insertion points. It turns out that within the Department of Defense, and even beyond, I think even at the national level, this tool, SPRUCE, has been recognized as one of the key insertion points in many different classes of systems. And this is actually a project that's going on at RI. They have some really large supercomputing resources up there. And so we're actually able to take the products both of the ASD initiative and of the Systems and Software initiative, integrate them into this architecture, and deploy them in real systems because many real Air Force systems are modeled through this environment. So we actually have a strategy for deploying this stuff and are doing so in real time. And I talked about the work with NASA, but the work with the Air Vehicles Directorate and some of the other folks who are doing things, even as diverse as distributed cloud infrastructures, are captured by this architecture in this environment. OK. As you can expect, there's a lot of collaboration between this program and a lot of the other programs just in the Math, Information, and Life Sciences group. These are just some of the ways we collaborate. So there's a lot of different ways we collaborate. I just highlighted the big collaborations because A, I run 2 of those programs, and B, there is a lot of back and forth with dynamics and control. We certainly do interact in terms of just understanding the verification methods between the analog and the digital systems, basically. OK, transitions. So I just told you about the Mars Science Laboratory and the next generation Mars rover. That's really cool. And we hope to maybe have a tech highlight on that before long. But beyond that, there's some other very interesting things going on. One of the things that I helped work on this last year under Systems and Software was a program with a company called Harmonia. And they're working with a tool called Hadoop. And I'm going to bring this back to the earlier talks that I did for complex networks. So basically, if I'm going to measure my infrastructure, and I'm going to do real-time analytics and learning on it, there's an interesting tool out there that's being deployed commercially and in academia to do that right now. So the API is called Hadoop, and the actual learning algorithms are another product which fits into Hadoop called Mahout. And if you want to know what those mean, just Google them. But basically, they're very powerful tools for real-time analytics of software infrastructure in real time. And these are open source. There's a real sort of grassroots GNU community that's building resources here. And in fact, some of my PIs in my other programs are actually using this architecture. So this helps me a lot by having people develop to this. But RI is actually looking at this for deployment in the context of very heterogeneous architectures like distributed tactical architectures, so that if my infrastructure is running, for instance, off a cloud, I can deploy real-time data analysis and runtime repair algorithms to those software modules in that infrastructure as conditions change. So literally, I can learn what's happening in my infrastructure and repair it dynamically by deploying it. Now, these tools are not up to that task. We're actually making them a lot more robust and hardening them and coming up with prototypes of our own. But this just gives you an idea that the commercial world thinks this way too. They're just not quite as far as we are in doing this. So I believe that the Air Force really does have a good leadership role in that. Certainly, Rockwell Collins is very interested in transitioning the SMT-based solvers and the low-dimensional verification methods to its avionics systems. And then, of course, we certainly have SBIRs and STTRs with this particular one is with intelligent automation. And basically, they're looking at really large infrastructures where you have mixed human-machine interfaces and trying to understand and identify what the machines do better and what the humans do better and dynamically assist and repair those. And that's it. I think I'm done. Thanks very much.